Have no fear, physics is here. It's the Kelvin Dueck Physics Show Extravaganza. And we're live.
The internet must wonder what my classroom is like. Oh well. We looked last day at distance versus time graphs. Do you remember what I said one of the key points to recognize was? What was the slope of a distance versus time graph? Or a displacement versus time graph? Velocity. What's an easy way to remember that? Put your pencils down, look up. I'm going to do a little sketch right here. This is my trick for memorizing graphs, and my trick for memorizing graphs is I don't. What I do know is how slope works. Slope is what over what? What's the little rhyming thing that you guys parrot back to me? Slope is what over what?
Rise over run.
Rise over run. So if you give me a distance time graph, what I actually do, if you ask me to talk about the slope, I look at the units. What are the units for distance measured in? Did I go on a rant about how you should always label your axes? I think I did, yes. What are the units for time measured in? So if you tell me that slope is rise over run, what you're also telling me, because the word over means divided by, is it's the y units, the rise, over the x units, the run. What are the units on the y-axis, Rob, my friend? In my little sketch right here behind me, what are the units on the y-axis? Did you say meters? That's the rise. Per. What are the units on the x-axis, my friend? And what I'm going to teach you this year is it's worth memorizing what units go with what concepts. Hey, what do I measure in meters per second? That's how I know the slope of a distance time graph is velocity. I've never actually memorized the graph itself. When you say distance time graph, I'm seeing that sketch that I just drew right there in my head. I'm seeing an M on the y-axis. I'm seeing an S on the x-axis, and I'm going, well, duh, it's meters over meters per second. It's velocity. That's real. That trick I just showed you, going to be really handy in Physics 12 when you'll have about 30 different graphs. No one memorizes them all. I had one kid who tried, and she gave up finally in about the end of November and caved and said, your method's better. I guess you can try memorizing them all. I'll just make up a new one then that I haven't told you yet. So if they ever ask me about the slope, look at the units. And that's going to come in handy today. We can define the average speed as the ratio of total distance to total time. Average speed is d over t. How do I know that that's speed average and not velocity average? If it was velocity average, what would I have drawn above the v? Error. In fact, you know what? Average velocity in this next box is defined in a similar manner. Average velocity is total displacement over time. And you'll notice I wrote in my notes here, you may sometimes see it written as delta x over t. We talked last class, we said the correct letter for displacement is a letter S, because that's what Sir Isaac Newton used, and he's the biggie, because in Latin, I think it's summa or something like that. We said we don't like the S, looks too much like a 5, looks too much like our unit for seconds, so I sheer away from that. If any of you are British, or if any of you go do schooling in Britain, they'll use S's. The next best really is X, because you're left-right, but we are going to be going up-down sometimes this unit, and I don't want to bring in a Y. You know what? I'm going to use the letter D for distance, D arrow for displacement. Oh, I did also say that time was always a change in, but Alex, you've already noticed I've stopped doing the delta in front of the T. It's, for Pete's sakes, always a change, and we're entering a little bit lazy. So average velocity, distance over time, average speed, velocity over time. Do you need to memorize this equation? I think it's on your formula sheet, but look, even more than that. Who remembers what I just said? What were the units for velocity? What did we say they were? Stop. What did you say? Meters, distance, per, divided by time. The equation is actually in the units. Kind of nice, kind of convenient. Example 1 says, find the average speed of an object that moves at 6 meters per second for 4 seconds, and then 100 meters. Did I hear a phone go off?
I heard it.
I think I did. We're going to pause my little video. I see somebody sweat. What's this question asking me to find? So average speed, I'll underline that. And that's going to be total distance divided by total time. Trish, I notice here I seem to see 2 trips. See it? So I'm going to divide my page into 3. I'm going to call this trip 1, trip 2, and my totals. So let's look at trip 1. What do we know about the first part of this trip? I see a 6. What's that? Look at the units. It's a velocity or a speed. It's meters. So you know what? I'm going to write I see a 4. What's that? Let's look at trip number 2. I see a 100. You see how I know that's trip 2? The word then? Yes? Mm-hmm. What's that 100? What are the units next to it? Meters. So it's a D, displacement or distance. I guess technically a distance. I see a 2.8. What's that? Now, here's what we said. We said average speed is going to be total distance over total time. I didn't write the word total in the previous form equation up there, but I did say it in the notes. It's total. It's total if you want average velocity. Okay. Can you tell me the total distance we traveled? Well, I know how far we traveled trip 2. How far did we travel in trip 2? 100. How far did we travel in trip 1? Don't know yet. So I bet you I can calculate it. How can I calculate it? Well, how did I get that? Well, that's sort of from Science 10, but look up, look up, look up. See this equation right here? What if I wanted to get the letter D by itself? What if I wanted to create a brand new equation, D equals? What else is on the same side as that letter D? Where is the T? What's the T doing to the letter D? Adding, subtracting, multiplying, or dividing? If I wanted to move it to the other side then, what would I do? Multiply. There is an entirely new equation hidden in there, and it's this one. And what I'm going to be teaching you over the next few days is something called formula manipulation. Formula manipulation, Zach, will allow you to memorize or be given 2 or 3 equations that actually has, well, about a dozen different equations hidden in there. This is one of the most single useful skills I'm going to throw your way. It's doing math with letters. It's scary at first. I'm going to say commit yourself to jumping into the pool. I'll help you stay your head above water, and eventually you will be swimming laps. If you try and avoid formula manipulation, if you always decide that you're going to plug numbers in first, I'm telling you, you're going to be hampered in your physics progression. So I'm going to push you. I think it's going to be 6 times 4. How far did we travel? So can you tell me over here what my total distance that we traveled is? I don't think you need a calculator, I hope, Ben. What plus what? 100 plus 24, which, Ben, in your head, without using a calculator, you're going to tell me what is 100 plus 24. Thank you. You didn't seriously reach for your calculator on that, did you? No, you, of course not. How could I falsely accuse you? Okay. The bottom is total time. How many seconds long was our first trip? 4. How many seconds long was our second trip?
We don't know yet.
Hey. See this new equation that we generated? What if I wanted yet another equation where the t was by itself? How would I get the t by itself? What other letter is on the same side as that there t there? V? What's the v doing to the t? Adding, subtracting, multiplying, or dividing? Multiplying? How would I move that v over, pray tell? So are you saying yet another equation that comes out of this would be distance divided by speed is time? 'Tis. I'm not going to give you all three on your formula sheet. I'm either going to give you this one or that one. I can't remember which. Or I might have given you a more complicated, useful, functional version, because this one only works if you're not changing speeds. I might have given you the one that includes acceleration. Can't remember. Anyways, I think I can find the time. That's distance divided by speed. That's 100 divided by 2.8. You get 35.7?
Yes.
Technically should go to 2 sig figs, but I'll go 35.7 for now. So I think the total time is 4 plus 35.7. And maybe you can even do that in your head without a calculator? 39.7. Now, I'll certainly live with a calculator for this. What is the average speed? Apparently, it's going to be 124 divided by 39.7. Looks like my average speed was 3. Let's see. Now I'm going to go look at my original data. How many sig figs? 3. How many sig figs? 3. How many sig figs? 3. You know what? Since we were dividing to find this, I know we added in the middle. Since we divided, I think I'll go to 3 sig figs. So I'm going to go 3.12. Units. Meters per second. I like that question. I like that question. I like that
Will it
question.
be on the test?
I don't know. I didn't say that, but you're the kind of student who notices when teachers emphasize certain things.
Mm-hmm.
Okay. Example 1 says sketch a graph of position, example 2 says, in example 1, sketch a graph of position versus time and velocity versus time. I think I gave you on the next page a place to do that, yes? Okay. It looks like this is kind of a bit of a weird one. I got 4 seconds. Eesh, you know what? I think I'm going to go like this. I don't like these numbers. I've just decided I'm going to change them next year, and I'm going to go to example 3, part A. Example 3, part A says, describe the motion of the object and then fill in the missing graph. And we're going to add some numbers to this. How about we make this number right here 12. Let's make a little note. This is in meters. Let's make a little note. This is in seconds. Let's say that this number right here is 4 seconds. And right here is 10 seconds. With me so far, Shaq? I want to take that. Well, first of all, what do we have on this graph? X. Hey, that's another symbol for distance versus time. Distance versus time. Right next to it, I have a speed or velocity versus time. And I'm going to eyeball it. Put yourself a 4 right about there. And put yourself a 10 right about there. What's the slope of a distance versus time graph? What did I say a few minutes ago? Do you remember? It's velocity because it's meters per second. What are we graphing here on the right-hand side? What's the right-hand graph a graph of? Okay, so can you tell me what's the slope of that line there? I tried to pick nice numbers. What's the rise? If we start at 0, how high are we at here? 12. What's the run? If we start at 0, where did we end up? Positive or negative? So what is 12 over 4 in lowest terms?
3.
Okay, I'm going to write here 3 meters per second. If I was graphing that as a velocity graph, I would be 3 meters per second high, because this time on the y-axis, my height is my velocity. How fast are we traveling 1 second in? Well, 1 second would be right about there. What's the slope right about there if you go up? You'd hit right here. What's the slope? Right there. I'll give you a hint. It's written in red.
3.
How fast are we traveling 2 seconds in?
3.
How fast are we traveling 3 seconds in?
3.
My velocity isn't changing. You know how I know? Because the slope is a straight line, not a curve. We call that a constant slope. So what I'm saying is, after 1 second, after 2 seconds, after 3 seconds, I think as a graph, it would be a horizontal line 3 high. Because on a distance time graph, the slope is the velocity or the speed. But on a velocity or speed time graph, the height is the velocity or speed. So far, so good? Okay. Let's do this second chunk. What's happening right there? How fast are we traveling? What's the slope?
0.
Ah. 0 meters per second. So I think that would look like a line, except I'll make it a straight line, not a slanty one. 0 meters per second high. I think that graph there is the graph, velocity or speed versus time, of the distance versus time graph that it goes with. So if you have, Emma, if you have a constant slope for distance time, that's going to be a horizontal line velocity. If you have a horizontal line, that's a slope of 0, that's a speed of 0, that's going to be a line 0 high. What if you had a slanty line going downhill, negative? That would be a line down here somewhere, negative. I didn't include that in this case. Is that all right? You did some of this in Science 10. We're being a bit more formal. B. Ooh. Now I'm giving you the velocity time graph, and we're going to see if we can go backwards and do the distance or displacement time graph. All right. You know what? Let's put some numbers on here. Let's call this 5 high. How about right here? Let's make it 10 seconds. I'll put time in seconds here. I'll put velocity in meters per second there. I thought you said you're always supposed to label the units. It was tough when we were doing the graphics. Does this height up look the same as this height down, or is this a little bit shallower? Are they the same or not? You guys got better eyes than me. My screen distorts stuff. No? So how about, let's make this -4 high, just below -5 high. Is that okay? So I'll put a little dot right here. -4. I think the lengths look about the same. Yeah, Jake? So what would be a good number to put right there? 20? Sure. All right. For the first 10 seconds, what is this horizontal line telling me? First of all, what kind of a graph is it? Kyle, what's on the y-axis? What letter? Okay, even better. Velocity, meters per second. What's on the x-axis? So, okay, So the height is telling me how fast we're traveling. What does a horizontal line mean? Does that mean we've stopped? Not here. Oh, constant speed. How fast? What would that look like over on this graph here? You know what? I think the first thing we'll do is we'll go 10 and 20. Okay, smarty peoples. Are you saying it would look something like that? Okay. Exactly how high would it have to hit so that when I went rise over run, I got 5 meters per second, like in my velocity? Ah, what? That would have to be a 50. Right? So we're going front and back now, forwards and backwards. A little more complicated than Science 10. Then what? Now we start heading backwards, apparently. What's my velocity here? Careful. -4. That is a direction component. That means my slope is going to be negative. Means my slope is going to be negative. Now, I don't... Oh, change colors, Mr. Dueck. I agree with down. Why didn't I touch the ground? Why didn't I do it quite as steep as my original? You know what? Let's even exaggerate it a bit more. We won't worry about trying to be the scale. Why would I go like that, not as steep as my original? In fact, you know what? I don't think I made it home. Because if I traveled for 10 seconds at 5 meters per second forwards, but I only travel for 10 seconds at 4 meters per second backwards, I don't think I'm making it home. Which is why my graph does not end at 0 high. In fact, can you figure out how high it would need to end at? What's my speed here? -4? How many seconds go by? How far would I travel? I think this is going to be 10. I think I get back to 10 meters from where I started from. Is that okay? This is complicated, I know. Acceleration is the rate of velocity change per second. In this section, I wrote, we're looking at constant acceleration, which means that the velocity change per second is constant. Units for acceleration are meters per second squared. It's meters per second, but we write meters per second squared. It's easier, Jeff. So, next page over. Let's see, we're going to get to here, and I think we're going to pause on example 5. Yeah. That works. Example 1. Suppose I'm accelerating at positive 1.25 meters per second squared to the east. There's my magnitude and direction. What does that mean if I start at rest? Or, what does that mean if I'm initially moving west at 2 meters per second? Well, see, acceleration is a vector, but it's very difficult to visualize its, or interpret its direction. Sorry, let's try that again. And the big difficulty is we tend to confuse it with velocity. I know my Science 10 students did last year. I know teachers that I've helped out with this at other schools tend to confuse velocity and acceleration. We talked about how your bodies are backwards accelerometers. Let's see if we can put this together. Example 4 says, fill in the chart for an acceleration of positive 1.25 meters per second squared east and 3 different initial velocities. The first one we have VI equals 0. So at time 0, we're stopped. At time 1 second, what will our velocity be, magnitude and direction, if we're accelerating at 1.25 meters per second squared to the east? Can you see it? 1.25. What about after 2 seconds? 2.5. Technically 2.50, but I want to make sure I fit the magnitude and the direction here, and I'm not going to worry about sig figs right now. What about after 3 seconds? What about after 4 seconds? What about, I think I spotted a pattern. And we're going to, by the way, find a shorter way to do this without building a chart, but we start out here, and then we're going to say it's got to be a shorter way that we can get straight to the answer. Like, what if I wanted to find your speed after 18 seconds? Would I have to fill in the previous 17? No. B. Here, VI was 2 meters per second east. So at time 0, we're 2 meters per second to the east. Start. We start accelerating to the east at 1.25 meters per second. After 1 second, how fast will I be traveling? Magnitude and direction. Sorry? Careful. I don't agree with the 0.75. 3.25? Yes? .25 meters per second? How about after 2 seconds? If we radar gun you now, how fast will you be traveling? 4.5 meters per second heading to the east, moving pretty quick. That's, let's see, my room is about 12 meters wide, so take you about 3 seconds to get across my room. That's about the speed of a fairly quick bike. Oh, what about after 3 seconds? 5.75 meters per second east. Now you're feeling the wind in your hair. You're going pretty good. C. This time we're going to start with an initial velocity of 2 meters per second west. What would be a good way to express west mathematically? I heard it, someone. I think we can say negative 2 meters per second, which is 2 meters per second west. Now, we're accelerating to the east, and we're going to call the east positive. So after 1 second, how fast are we traveling now? You could either say negative 0.75 meters per second, or you could say 0.75 meters per second, still heading west. Which one's easier to write? The negative. And that's going to be the notation we're going to drift into. Sometimes we'll pull out east, west, north, and south, but usually it's just going to be positive and negative, and we'll clue in what we're talking about. Ah. Okay, after 2 seconds, how fast will you be traveling? Darian, what? Let's see. We have 1.25 meters per second of acceleration. So 0.75 of that is going to go into bringing me to a stop. And how much do I have left over? I think I'm going to be going, or you could just say positive 0.5. Yeah. In fact, somewhere between 1 second and 2 seconds, that's when we turned around. That's when we came to a stop and changed direction. 3 seconds. Now we're back into more familiar territory. I think it's going to be 0.5 plus 1.25. I think it's going to be 1.75 meters per second east. Yep.
Why does I know they're negative? Do they mean a direction?
Well, we have two options. You can include a direction to the west, or you can put the negative. Don't do both, because what direction is negative west? I think I would argue two negatives make a positive. That's an east. So you can use one or the other. Zach, I'm going to drift towards the negative notation. It's less writing, it's less confusing, and that way we'll almost always just let to the right on our paper be positive and to the left on our paper be negative, just like on a graph. We'll let up be positive and down be just like on a graph, unless it really serves our purposes to change it, in which case we will once in a while, but not very often.